The potential of nature-based solutions in urban heat mitigation and building energy savings. Siki Jia, Chihao Wang, and Yuhong Wang introduction. Given the frequency and severity of heat waves and urban heat islands, UHI, there has been a growing awareness of the UHI and urban thermal environment. Ketterer and Matsarakis, 2015. Kim and Brown, 2021. Su et al., 2022. The increasing urban heat not only traps atmospheric pollutants, deteriorates the conditions of living environments, and increases energy consumption. Hareth et al., 2018. But it also affects health, leisure activities, and well-being of urban dwellers. Doik et al., 2014. Faisa et al., 2014. Halder et al., 2021. With more than half the world's population currently residing in cities, and this number expected to rise to around 70% by 2050. Proferoyu et al., 2020. Ritchie and Roser, 2018. Combating the adverse effects of urban heat has become a pressing global issue for both the environment and human beings. Consequently, it is crucial to develop effective heat mitigation solutions to alleviate these challenges. Aram et al., 2019. Wang et al., 2021. Nature-based solutions, NBS, are increasingly recognized as effective measures to address the challenges of UHI and heat waves by providing cooling services. Laforteza et al., 2018, Su et al., 2022, and therefore help to increase energy efficiency. It can foster and simplify implementation actions in urban landscapes by taking into account the service provided by nature. Kabish et al., 2017. Moreover, it is highlighted that NBS can be cost-effective and that benefits range from environmental protection to creating jobs that stimulate innovation for a green economy. Examples of NBS include provision of urban green space such as parks, street trees, and green infrastructure, e.g. green roof, green facade, that may ameliorate high temperature in cities or regulate air and water flows. Gill et al., 2007, Yamamoto, 2006. In this research, the performance of 3 commonly used NBS in urban heat mitigation and building energy savings are introduced, including green roof, evaporative pavement, and street trees. Numerous studies have shown that NBS are effective in heat mitigation and energy use reduction. A. Niak, 2001, Castleton et al., 2010, Romeo and Zinzi, 2013, Zhang and Wang, 2020. While their efficiency is significantly influenced by local climate conditions and building characteristics. However, most of those studies have only considered a few selected buildings in case studies or have focused primarily on the summer season. Costanzo et al., 2016, He et al., 2020, leading to a lack of research on how variations in ambient climate and built environment influence the energy-saving potential of these technologies. Building energy consumption is greatly susceptible to meteorological feedback, which refers to the dynamic interactions between the building and the surrounding environment, particularly local weather conditions. Li et al., 2019. The heating, cooling, and ventilation requirements of a building are influenced by meteorological feedback, which can have a significant impact on energy consumption. Wang et al., 2011, Yu and Hien, 2006. Accurate prediction and modeling of meteorological feedback is crucial for optimizing building energy performance and reducing energy consumption. However, most existing building energy simulation models use typical meteorological year, TMI, weather files to represent historical and current weather conditions. Fumo, 2014, Hosseini et al., 2020, while failed to incorporate ambient microscale climatic conditions and ensure accurate results in energy simulations. Overall, a comprehensive study that compares these typical NBS in different climate settings is called for. To improve the model accuracy, this study proposes a new integrated approach to study the potential of building energy reductions by different NBS. This approach combines climate change modeling and building energy simulation to quantify the effect of climate change on building energy demand. The research objectives include 1. To evaluate the effectiveness of NBS in urban heat mitigation. 2. To evaluate the effectiveness of NBS in building energy savings. 3. To identify the influencing factors affecting the performance of typical NBS in different urban built environments and climates. The results of this study can help policymakers and urban planners make informed decisions about the implementation of NBS in their respective cities. leading to greater sustainability and resilience of urban areas in the face of climate change. Furthermore, the study contributes to advancing the scientific understanding of the role of NBS in urban planning and highlights the importance of developing solutions that are tailored to specific local conditions. Nature-based solutions for urban heat mitigation and building energy savings. In this research, the performance of 3 commonly used NBS in urban environment was evaluated, including green roof, evaporative pavement, and street trees. This section covers the mechanism, effectiveness, advantages, and limitations of each NBS. Green roofs. A green roof is a layered system that includes a waterproofing membrane, growing medium, and vegetation layer. Castleton et al., 2010. It has become an increasingly popular design strategy for improving urban environments due to its numerous environmental benefits, including reducing stormwater flow, improving air quality, and mitigating the urban heat island (UHI) effect. Barrio, 1998. Berardi, 2016. Green roofs are widely recognized to mitigate increased urban temperatures, particularly in hot climates, where they can reduce temperatures to more comfortable levels. Razagmanesh et al., 2016. During winter conditions, they offer effective thermal protection by providing high insulation levels that strangle heat flux. He et al., 2017. Theodosio, 2003. Green roofs can also lower cooling energy costs by 32% to 100%. Suska et al., 2011, while reducing heating energy demands by 23%. Zhao et al., 2015. Green roofs can be classified into 2 types based on their purpose and characteristics: extensive green roofs, EGR, and intensive green roofs, IGR. Townshend, 2007. EGR is covered with grass only and is designed to be self-sustaining. In contrast, IGR is usually associated with rooftop gardens and requires skilled labor, irrigation, and constant maintenance due to the deeper soil depth needed for growing trees and other vegetation. Bianchini and Hewage, 2012. IGR typically has thicker growing media and higher canopy density, resulting in higher levels of evapotranspiration and shading than EGR. This results in lower outdoor surface temperatures and better cooling effects. Castleton et al., 2010. Silva et al., 2016. However, IGR requires higher capital costs and technical expertise for installation and maintenance compared to EGR, which offers more economic benefits. Townshend, 2007. Figure 7.1 shows the appearance of both types of green roofs. Figure 7.1, extensive green roof and intensive green roof. Nevertheless, although urban heat mitigation through roof-level strategies has often been investigated, the effectiveness of heat mitigation strategies in improving the pedestrian-level thermal environment has been questioned. For instance, because of the height of roofs, some researchers believed that the pedestrian-level cooling effects of green roofs are negligible. Chen et al., 2009. Zulch et al., 2016. In contrast, the street-level heat mitigation strategies are believed to be more effective in improving pedestrians' thermal comfort through shading, evaporation, and evapotranspiration. Morakinyo Dahanayak et al., 2017. Talagani, 2018. Evaporative and water-retentive pavements. Evaporative and water-retentive pavements allow water to pass through their material voids, thereby facilitating its penetration into the soil. These pavements rely on evaporation of the water for the maintenance of a desirable thermal environment. Higher moisture contents and increased watering can help keep the pavement surface cooler. To achieve their water-retentive and permeable properties, these pavements eliminate finer particles from their structure or replace them with more porous materials such as pozzolans, slag, fly ash, or silica fumes. Mohajarani et al., 2017. The porosity of these materials imparts a lower albedo compared to impermeable counterparts and enhances convective fluxes to the atmosphere by increasing the effective surface area via higher void content. Hazelbach, 2009. Santamoris, 2013. According to ITO 2006, water-retentive pavements can reduce surface temperatures by up to 16 degrees Celsius and air temperatures by approximately 1 degree Celsius, contributing to the UHI mitigation. Another study on surface heat budgets demonstrated that adding water-retaining materials to asphalt and cement concrete surfaces significantly reduced sensible heat flux at rates of 150 watts per meter and 100 watts per meter, respectively. Takabayashi and Moriyama, 2012. The effectiveness of evaporative and water-retentive pavements may be limited by climatic conditions. Santamoris, 2013. They are more suited to warm and humid climates where rainwater is a significant factor in cooling pavement surfaces. Figure 7.2 shows the progress of how water-retentive pavements cool the environment. Street trees. Urban areas can benefit from large tree or shrub-type green spaces as they provide notable cooling through shade, evapotranspiration, and increased albedo. Wang et al., 2021. The cooling effect and thermal comfort improvement of trees depend on factors such as leaf area index, tree height, trunk height, and spatial configuration of trees. Moraquinho, Kong, et al., 2017. Tan et al., 2016. Zhou et al., 2017. Numerous studies have highlighted the effectiveness of implementing trees for outdoor heat mitigation in high-density urban settings. Moraquinho, Kong, et al., 2017. Tom et al., 2016. For example, Chung and Jim, 2018, compared the cooling effects of a tree and a concrete shelter, identifying that the tree provides significantly better cooling effects than the shelter with the mean daytime air temperature reduction at 0.6 degrees Celsius and the maximum daytime air temperature reduction at 2.1 degrees Celsius. Chung and Jim, 28A. Another study used high-resolution satellite data of 293 European cities to investigate the effectiveness of urban trees in mitigating urban heat. Results showed that the surface temperature observed for urban trees is on average 0 to 4 K lower in southern European regions and 8 to 12 K lower in Central Europe. Schwab et al., 2021. Increasing tree canopy in open and exposed streets should be given priority to achieve the greatest improvement in outdoor thermal comfort. Tom et al., 2016. However, the cooling effect of small green space with few trees or shrubs and grass-type green space has been questioned. Some studies have suggested that these types of green spaces are more susceptible to urban and anthropogenic influences, which may increase sensible heat gain instead of providing cooling. Wang et al., 2021. Figure 7.3 shows an example of the typical design of street trees. Figure 7.2, water-retentive pavement. Methodology assessment of thermal comfort, mean radiant temperature. To objectively assess the thermal comfort level of a space, 4 crucial meteorological variables that govern the human energy balance and outdoor thermal comfort are typically utilized. These include air temperature, TA, relative humidity, RH, wind speed, VA, and mean radiant temperature, TMRT. Particularly, TMR is a critical metric for human thermal comfort assessment. Mayer and Heppe, 1987. Thorsen, Lindberg, et al., 2007, for it is a quantity linking the radiant energy transfer between a human body and surroundings to which the body exposed. Ashray, 2013. While all other meteorological parameters can be obtained from on-site sensors, there are 2 common methods for directly measuring TMR, the integral radiation method and the globe thermometer method. Thorsen, Hanjo, et al., 2007. The integral radiation method, which was proposed by Huppe in 1992, Hupp 1992, has been widely recognized as the most accurate TMR measurement method. Thorsen, Lindberg et al., 2007, VDI 1998, Walikowicz et al., 2015. It is an experimental method that involves the measurement of shortwave and long-wave radiant flux densities emitted from the entire 3-dimensional environment. Huppe, 1992. Manavi and Rajasekar, 2020. However, it is difficult to undertake multi-point observations by this method in outdoor experiments with respect to the high cost and complexity of measurement setup. Therefore, the observations using the integral radiation method are often used as a reference to compare or modify the results of other methods. Chen et al., 2014, Crank et al., 2020, Delito Volaro et al., 2013. Another commonly used method to obtain an estimate of TMRT directly is the globe thermometer method. The black globe thermometer method has been in use since it was first developed in the 1930s and then quickly gained attention due to its simplicity. Bedford and Warner, 1934. Referring to Kuhn et al. Kuhn et al., 1970. Assuming the globe thermometer is in equilibrium, the globe temperature, which is expressed as the weighted average of radiant and ambient temperatures, reflects the convective and radiative heat exchange around the black globe thermometer. The globe thermometer method was initially developed to measure indoor radiant temperature. For outdoor use, an empirical equation is required to predict TMRT based on additional parameters including the wind speed and air temperature. Chapter 7, Equation 1. T sub MRT equals open parentheses, T sub G plus 273.15 close parentheses to the fourth power, plus 1.1 times 10 to the eighth multiplied by V sub A to the 0.6 power divided by D to the 0.4 power, multiplied by open parentheses T sub G minus T sub A close parentheses, all raised to the 1/4 power, then minus 273.15. Where Tg is the globe temperature, degree C, Va is the air velocity, Ta is the air temperature, degree Cc, D is the globe diameter millimeter, and is the globe emissivity. However, the globe thermometer method has some shortcomings in outdoor applications. For example, previous studies revealed the unsuitability of the globe thermometer for TMRT measurement in an outdoor situation. Given the constantly changing radiative fluxes, and air velocity may prolong the time to reach equilibrium, Spagnolo and De Deer, 2003. Outdoor thermal comfort indices. Researchers have dedicated substantial effort towards developing metrics for quantifying human thermal comfort. Herman and Matsarakis, 2010. Hope, 1999. Makarami et al., 2012. Human thermal comfort is described as a state of mind that reflects satisfaction or dissatisfaction with the surrounding environment. Abdelghani et al., 2013. An individual's thermal state is affected by microclimatic conditions such as wind speed, temperature, humidity, and the positions of sun and shade. Cheng et al., 2011. Comfort, 2003. Lai et al., 2014. To assess outdoor thermal comfort, several indices integrating environmental factors and the energy balance of the human body have been developed. Shi et al., 2012. Some examples of these indices are the predicted mean vote, PMV, physiological equivalent temperature, PT, and Universal Thermal Climate Index, UTCI, Fang et al., 2019, Lai et al., 2014, Provencal et al., 2016. Although all of these indices have been applied to assess human responses to the environment, the use of steady-state indices, e.g. PMV, may lead to estimation errors for pedestrians in an outdoor environment where dynamic thermal adaptation and transient process are involved. For instance, studies by Nicolapoulou et al., 2001, and Lai et al., 2014, found significant discrepancies between a person's subjective thermal satisfaction and objective thermal states described by PMV. Hence, recent studies commonly use PET and UTCI as outdoor thermal indices, Chung and Jim, 28bb. Both indices simulate dynamic heat transport within the body and the heat exchange between the body and its environment, Fiala et al., 1999, 2001. Compared to the two-node models used for PET, multi-node models used for UTCI provide more detailed simulations of the human body, predicting both overall, whole body, and local, multi-node, physiological responses. Fang et al., 2019, Jia and Wang, 2021, Raka, 2015. Therefore, this study employed UTCI to represent outdoor thermal comfort. Microclimatic modeling ENVI-MET. For simulating the meteorological parameters and universal thermal indices, ENVI-MET has been applied to account for the thermal exchange of every location in the environment with fine resolutions. ENVI-MET is a computational fluid dynamics, CFD, based microclimate and local air quality model. ENVI-MET is capable of calculating both surface temperature and air temperature of different heights within the interval times for 24 to 48 hours. Hien et al., 2012. Key input parameters include weather conditions, initial soil wetness and temperature profiles, structures, the physical properties of urban surfaces, and plants. Berardi, 2016. ENVI-MET can simulate the long-wave and short-wave radiative exchange within the plants, the plant canopy effects on convective heat transfer, evapotranspiration from soil and plants, heat conduction in the soil layer, and moisture-dependent thermal properties. Saylor, 2008. Yang et al., 2019. Zulch et al., 2016. ENVI-MET consists of a one-dimensional, 1D, boundary submodel, which is used to calculate the inflow profile and top boundary, a three-dimensional, 3D, atmospheric submodel, which is the main model, and a 3D, 1D soil submodel. Huttner, 2012. Flow simulation in the atmospheric model is based on the Reynolds average Navier-Stokes RANS equations, Osiro and Arrizabalaga, 2016, and Yamada and Meller Yamada and Meller, 1975, is chosen as the turbulence model. Further details of NVMet can be found in the literature. Ali Tudert and Mayer, 2006, Bruce and Fleer, 1998. Scenario development. The computational domain in this study is set as x times yz equals 250 meters times 250 meters times 200 meters. Both the buildings and streets in the study area are carefully modeled. Key input parameters include weather conditions, initial soil wetness and temperature profiles, structures, the physical properties of urban surfaces, and plants. Berardi, 2016. 3 types of land cover are considered for the walkways: soil, permeable surface using grasscrete paver, and asphalt pavement. Default albedo values are used for each type of land cover. The buildings, height, 30 meters, and trees, height, 5 meters, canopy width, 5 meters, are distributed on these land cover types. Additional simulation details are shown in Table 7.1. The base scenario represents the current outdoor microclimate, urban layout, and surface conditions of the study area. Additional simulation scenarios are developed for evaluating the influences of different types of heat mitigation strategies on outdoor microclimate and thermal comfort. The details of each simulation scenario are shown in Table 7.2, and the layouts of scenarios are displayed in Figure 7.4. The influences of 4 types of heat mitigation strategies, EGR, ST, and PP, and the reference RF on outdoor microclimate and thermal comfort are evaluated based on the outputs of ENVIMET, including surface air temperature, TA, mean radiant temperature, TMRT, relative humidity, RH, and wind speed, VA. Table 7.1, ENVIMET simulation details. Table 7.2, description of simulation scenarios. Figure 7.4, the layouts of simulation scenarios. A, reference REF. B, extensive green roof, EGR, and intensive green roof, IGR. C, permeable pavement, PP, and D, street trees. Validation of the meteorological outputs. The general validity of the ENVIMET model was evaluated from an experimental site in Hong Kong, Figure 7.5a. The experimental area is 100 meters times 100 meters with a grid resolution of 0.5 meters. 2 sets of experiments were conducted under sunny conditions on different dates and seasons: October 29 to 31st, 2020, April 3 to 5th, 2021, at the same site. The diurnal profiles obtained from the 3-day observations were used to validate the model. To measure and record the background weather parameters, a Kestrel 5400 weather station, Nielsen Kellerman Co., USA, was set up at a height of 1.5 meters above the ground level, Figure 7.5b. The following parameters were measured: air temperature, range minus 29 to 70 degrees Celsius; globe temperature, TG, range minus 29 to 70 degrees Celsius; relative humidity, RH, range 10 to 90%; wind speed, VA, range 0 to 40 meters per second; and wind direction, range 0 to 360 degrees Celsius. The mean radiant temperature, TMRT, based on the globe thermometer method, Chen et al., 2014, Marotra et al., 2019, Standard and ISO, 1998, Tan et al., 2013, was calculated using the globe temperature, air temperature, and wind speed data. In the second experiment, another Kestrel weather station was installed at the inlet boundary of the modeled area to measure the inlet wind speed. The global radiation data was collected with a CMP3 Kip and Zonin pyranometer to calculate the solar radiation adjustment factor in ENVIMET. The hourly mean values of air temperature and relative humidity during the modeled time period were used for simple forcing in ENVIMET to perform the simulations. Figure 7.5. The experimental site, A, and experimental setup, B. The outputs were compared with the diurnal profiles of measured meteorological variables. Table 7.3 provides 2 error terms obtained from ENVIMET and field measurements: the mean absolute error, MAE, and the error range. The relatively low MAE values in both experiments indicate that the prediction results for the 4 meteorological parameters are partially accurate. ENVIMET was then applied to the scenario analysis in this study. Table 7.3, estimation errors of meteorological parameters in 2 experiments. Building Energy Simulation Energy Plus. This research proposes an integrated modeling approach that combines ENVIMET and a building energy simulation program, iNergy Plus. Figure 7.6 illustrates the development of the integrated modeling approach. The model first simulates microclimatic conditions in various urban built environments under different climates using ENVIMET. For the model inputs, the climate conditions incorporate the climates of 6 evaluated cities, while the built environments incorporate the typical urban building types based on the local climate zone (LCZ) system. Case studies were conducted in 6 selected cities in different climatic zones around the world, including Cairo, Hong Kong, Seoul, London, Los Angeles, and Sao Paulo. The forcing weather data required for the simulations was obtained from Energy Plus Weather, EPW, files for each city. ENVIMET can generate much more detailed meteorological outputs, e.g., ambient temperature, relative humidity, wind speed, and reflectance, compared to the region-level EPW files. The outputs of ENVIMET are then used to configure Energy Plus by modifying the TMY weather inputs. Based on the microscale environmental parameters, the detailed building energy use is simulated for different modeled environments. Energy Plus is an open-source simulation program used for estimating building energy use, including heating, cooling, ventilation, and lighting. Crawley et al., 2001. It enables users to model buildings with mechanical and electrical systems that have integrated thermal controls and perform simulations based on real building descriptions. Morakinyo, Dahanayak et al., 2017. Energy Plus has been widely used to help optimize building energy performance and improve indoor thermal comfort while reducing energy consumption. Fumo et al., 2010. Figure 7.6, Development of the Integrated Modeling Approach. The integrated modeling framework described in this research offers a powerful tool for conducting detailed observations and simulations of local physical environments and meteorological conditions. This approach can lead to more accurate estimations of building energy use compared to traditional modeling methods. In this study, the framework is then applied to a set of scenarios after validation. The scenario development involved modeling the building energy use with or without energy-saving solutions in different ambient climates and urban built environments. By comparing the results of these simulations with those of the baseline scenarios, we are able to determine the effectiveness of cool and green roofs for reducing building energy use in different environments. Scenario development. Among the 3 evaluated NBS, i.e., green roof, permeable pavement, and street trees, only the building energy-saving performance of roof-level strategies, i.e., green roof, was evaluated. For scenarios incorporating the effect of ambient climate, the distinct climate of 6 typical cities around the world was incorporated into scenarios evaluating the energy-saving performance of green roofs. For scenarios incorporating the effect of urban built environment, 6 scenarios incorporating different urban built environments were constructed according to the LCZ system. Stewart and Oke, 2012, Zheng et al., 2018. LCZs are being used in the numerous studies focusing on temperature, rainfall, and other environmental variables. Das and Das, 2020, Patel et al., 2023, Yang et al., 2021, Yang et al., 2022. In this study, each scenario corresponds to a different LCZ, including 1. Scenario A, LCZ1, compact high-rise environment. 2. Scenario B, LCZ2, compact mid-rise environment. 3. Scenario C, LCZ3, compact low-rise environment. 4. Scenario D, LCZ4, open high-rise environment. Scenario E, LCZ5, open mid-rise environment. And 6. Scenario F, LCZ6, open low-rise environment. Table 7.4 presents geometric and surface cover properties for each LCZ. The layout corresponding to each LCZ was modeled in ENVIMET. The computational domain in this study was set as XY's 200 meters to 125 meters, with grid cells of 5 meters. 2 types of land cover, natural surfaces, covered by soil, and concrete pavement, were considered to characterize the pervious and impervious surfaces within the modeled space, respectively. Default albedo values were used for the different types of land cover. For modeled spaces of compact urban densities corresponding to LCZs 1 to 3, the building surface fraction was 60%, while the impervious surface fraction was 40%. A total of 7 buildings were uniformly distributed on the concrete surfaces, and there was no previous surface among these 3 modeled spaces. For LCZs 4 to 6, 6 buildings were included in the modeled environment, with a total building surface fraction of 30%. The impervious and pervious surface fractions were 40% and 30%, respectively. Trees, height 10 meters, and shrubs, height 0.5 meters, were uniformly distributed on the natural surfaces with a canopy width of 10 meters. Assuming an average floor height of 3 meters, the building heights for all buildings within the modeled space ranged from 30 to 60 meters, 10 to 20 story height. For LCZs 1 and 4, 15 to 24 meters, 5 to 8 story height for LCZs 2 and 5, and 3 to 9 meters, 1 to 3 story height for LCZs 3 and 6. Table 7.4, Geometric and Surface Cover Properties for each LCZ validation of the building energy use. The proposed methodology was validated using a building energy dataset obtained from the U.S. Department of Energy's Building Technologies Office, Luo et al., 2022. The target building is a medium-sized office building, i.e., Building 59, located in Berkeley, California. The building has 4 floors, only the top 2 floors are the office floors, and a conditioned space of 10,400 millisquares. The building's roof is composed of a white single-ply PVC roofing membrane installed on a concrete roof deck. Figure 7.7 depicts the appearance and layout of the model building. The dataset comprises hourly data of whole building and end-use energy consumption, HVAC system operating conditions, outdoor and indoor environmental parameters, and occupant data. The dataset covers a period of 3 years from 2018 to 2020. To validate the accuracy of the proposed integrated method, we first simulated the diurnal profiles of energy consumption in the reference office building for a typical winter day and summer day. We then compared the simulated hourly profiles with the observed hourly building energy use on those 2 days. After validation, the proposed method was used to simulate building consumption in various scenarios. The diurnal profiles of energy consumption in the reference office building were simulated on 2 typical days. The day with the minimum daily ambient temperature, January 26th, and the day with the maximum temperature, June 18. Figure 7.8 shows the accuracy of the simulated hourly building use by the integrated modeling approach on both days, along with the building energy use predicted by the conventional method with inputting the regional weather data as a comparison. Figure 7.7, Appearance and Layout of the Model Building. Figure 7.8, Accuracy of the hourly energy use simulation. A, on a typical winter day. B, on a typical summer day. The proposed method using micro-level weather data is capable of accurately simulating building energy use at a high temporal resolution. On a typical winter day, figure 7.8a, the proposed method reduces the root mean square error, RMSE, from 7.25 kilohours, 1.27%, with the conventional method to 4.96 kilohours, 0.87%. On a typical summer day, figure 7.8b, the proposed method also outperforms the conventional method with an RMSE of 6.08 kilowatt-hours, 0.46%, which is 3.09 kilowatt-hours lower than that of the conventional method, 0.69%. This method has further potential applications for building energy simulations in various climates and built environments after further validation. Results performance of nature-based solutions in urban heat mitigation. The heat mitigation potentials of the different types of heat mitigation strategies are analyzed. Figure 7.9 presents the diurnal air temperature, mean radiant temperature, and UTCI at the pedestrian level at a height of 1.5 meters of the walkways for the 5 simulation scenarios, 1 reference and 4 NBS. Note that the temperature shown in the figure is the average temperature of all the points on the walkways for each simulation scenario. The figure reveals the effectiveness of different types of heat mitigation strategies at improving the thermal environment, especially between 13 and 1700 when it is the hottest. All evaluated NBS can cause some reductions in air temperature. Compared with the reference, street trees cause a maximum reduction in air temperature and mean radiant temperature by 0.27 degrees Celsius and 4.23 degrees Celsius, respectively. According to Figure 7.9c, street trees also result in the lowest values of UTCI during the daytime, with a maximum UTCI reduction of 0.8817 degrees Celsius at 1100. The UTCI values of all other heat mitigation strategies are only slightly lower than those of the reference. At night, there is almost no difference in UTCI values among all of the scenarios, except for the slightly increased values under the ST scenario. Notably, the thermal environment may affect air conditioning use in the neighborhood, as lower environmental temperatures may be associated with less heat emission from air conditioning. This factor, however, is not incorporated into estimates of UTCI values. Next, the distributions of UTCI reductions compared to the reference are shown in Figure 7.10. UTCI reduction value is calculated by subtracting the UTCI value of the simulation scenario from the reference value at the same position. All of the values in the figure are obtained from the simulation results at 1600 when the reference's UTCI reaches a maximum. Figure 7.10 reveals that there is an interactive effect between the location and type of heat mitigation strategy. For the roof level NBS, EGR, and IGR, see Figure 7.10a and b. The effects of green roofs on improving pedestrian-level thermal comfort are more noticeable along the EW directions of buildings, and the thermal comfort improvement is more obvious in the SW corner of the study area. In the PP scenario, Figure 7.10d, the biggest UTCI reductions occur along EW-oriented walkways in the southern part of the study area. The figure also suggests that adding street trees causes the most significant reductions in UTCI over the entire neighborhood. The improvements to thermal comfort are remarkable in some street tree locations, corresponding to the dark blue pixels shown in Figure 7.c. Figure 7.9, diurnal profiles of the performance of NBS in heat mitigation. A. Air temperature reduction. B. Mean radiant temperature reduction. C. UTCI reduction. Figure 7.10, distributions of UTCI reductions for all NBS. A. EGR. B. IGR. ST. D. PP. Performance of nature-based solutions in building energy savings. The proposed integrated modeling framework was used to simulate the energy use of buildings in 6 cities with varying local climates over a 1-year period. We compared the energy consumption of buildings installing green roofs to a reference building using concrete roofs without any energy-saving strategies. The comparison results are shown in Figure 7.1 which displays the annual reduction of both cooling and heating energy by green roofs in each city. Figure 7.1 and B show the effects of climate and urban built environment characterized by LCZ on both cooling and heating building energy savings by green roofs, respectively. Observed from Figure 7.11a, the mean reduction of green roofs ranged from 63.38% to 83.21% among the 6 evaluated cities. The best cooling energy reduction effects for green roofs were observed in London and Sao Paulo, respectively, with mean reduction rates of 78.63% and 83.21% across different built environments. The heating energy reduction effect of green roofs was relatively significant in Sao Paulo, Cairo, and Los Angeles, with mean reduction rates of 87.92%, 85.65%, and 80.37%, respectively. Observed from Figure 7.11b, urban built environment plays a crucial role in determining the green roof energy saving performance. Significant variations in both cooling and heating energy reductions were observed in different LCZs, with mean reduction rate ranging from 38.3% to 100% for cooling energy reduction and 47.4% to 100% for heating energy reduction. Notably, LCZs 3 and 6, characterized by low-rise buildings, can achieve nearly zero annual energy demands for cooling or heating by installing green roofs. The results indicate that the energy-saving effectiveness of green roofs largely depends on the climate zones they are applied in and the urban built environment. Discussion the effectiveness of NBS in cooling the environment and improving thermal comfort. The simulation results show the effectiveness of different NBS towards cooling the environment and improving thermal comfort. Trees and vegetation seem to be the key strategy to reduce temperature and improve thermal comfort in hot summer conditions through their combined effects of shading and evapotranspiration. Ali Tudor and Mayer, 2007. Makaremi et al., 2012. Wang and Akbari, 2016. At night, the mean radiant temperature of the street tree ST scenario is higher than that of the reference. This may be explained by the subdued evapotranspiration of vegetation at nighttime. Peng et al., 2020. Although many existing studies conclude that green roofs have no cooling effect on pedestrian-level microclimate, Chen et al., 2009, Zulch et al., 2016, this study finds that there is some cooling brought about by roof-level heat mitigation strategies, especially by the intensive green roofs, IGR. The more voluminous biomass and extended canopy areas of IGR may provide some passive cooling at the pedestrian level through evapotranspiration. Peng and Jim, 2013. Figure 7.11, Annual Cooling Heating Energy Reductions by Green Roofs. A. In different climates. B. In different LCZs. Among all evaluated types of NBS, street trees cause the biggest reduction in average UTCI, with a maximum reduction of 0.8817 degrees Celsius at 1100, while the extensive green roof EGR has the least effect on UTCI. For the ST scenario, UTCI reductions are the most significant at the locations where the trees are planted. Other types of heat mitigation strategies also lead to UTCI reductions, but to a lesser extent than street trees. These other mitigation strategies also show some locational variation in UTCI reduction. For example, permeable pavement, PP, shows more noticeable effects at the paths located in the south region of the study area, and IGR causes more obvious changes along the EW directions of buildings. Therefore, location effects may be considered when planning green infrastructure. Although adding street trees is beneficial, its implementation in well-established, densely populated urban areas may face some challenges. First, there is often less land space than is required to plant a tree and have it develop a mature root system. Second, as a city with a large number of tropical cyclones, falling trees often disrupt traffic and pose a public hazard in Hong Kong. These challenges necessitate the proper choosing of trees and planting strategies. In addition to street trees, some studies also recommend the use of protrusions from facades or buildings located next to the streets to reduce thermal stress exposure and improve walkability. Rodriguez Algeciras et al., 2017. Such features are not evaluated in this study due to the difficulty of retrofitting existing buildings. The effectiveness of green roofs in reducing building energy use. In hot and sunny regions and relatively cold regions, green roofs can reliably reduce energy demand throughout the year. This finding is consistent with existing literature. Costanzo et al., 2016, Silva et al., 2016, Yang et al., 2018, Zinzi and Agnoli, 2012. Due to the extra insulation soil layer of green roofs, which tends to keep heat stored in the buildings, green roofs can provide heating energy-saving benefits as well in cities with colder climates. However, in some warm regions with cloudy or rainy climates, where greenery has less cooling effect due to reduced rates of evaporation and transpiration of plants, the use of green roofs may be carefully considered. Under this case, cool reflective pavements with higher albedo, e.g., cool roofs, may be adopted for reducing cooling energy use of buildings. The kinds of strategies reduce surface and air temperature in the surrounding environment, mainly by increasing the percentage of reflected solar radiation due to an increase of reflectivity. Mohajirani et al., 2017, Wang et al., 2021. In addition, since urban built environment can significantly affect the performance of green roofs, the possible overshadowing effects of adjacent buildings should be carefully considered and modeled. Some studies also recommend conducting solar simulation before implementing these mitigation strategies. Wang et al., 2021. When deciding on the implementation of green roofs in the long-term development of buildings, it is also important to consider not only their effectiveness in reducing energy consumption, but also their economic and environmental benefits. For example, compared to cool roofs, green roofs provide additional benefits such as reducing urban heat island effects, improving air quality, increasing water permeable surface, enhancing stormwater management, and improving the durability of roof materials. Hamel et al., 2021, Meng et al., 2022, Wang et al., 2021. Especially in high urbanized regions, the application of green roofs can bring more ecosystem service benefits to both urban environments and humans. Conclusion. Given the growing issue of urban heat islands, UHI, and increasing global building energy demand, this study aimed to assess the effectiveness of various nature-based solutions, NBS, including green roofs, permeable pavements, and street trees, in mitigating UHI, improving thermal comfort, and reducing building energy consumption. To improve modeling accuracy, this study developed an integrated modeling approach that combines climate change modeling and building energy simulation to quantify the impact of microclimate change on building energy demand. Through scenario analysis, the impacts of each NBS scenario on air temperature, TA reduction, mean radiant temperature, TMRT reduction, and Universal Thermal Climate Index, UTCI reduction, were analyzed. Our results show that ST scenario was the most effective in reducing TA, TMAK, and UTCI. However, the effectiveness of each type of NBS varied depending on the location within the study area, highlighting the importance of considering urban forms in infrastructure planning. To further investigate the potential for NBS to reduce building energy consumption, we evaluated the energy-saving performance of green roofs across different ambient climates and urban environments in 6 global cities: Cairo, Hong Kong, Seoul, London, Los Angeles, and Sao Paulo. In summary, this study provides important insights into the effects of local ambient climate and urban built environment on the performance of typical NBS in UHI mitigation and building energy savings, which can inform the selection and design of appropriate NBS for different urban contexts to cope with climate change. Limitations of the study, however, include the fact that this paper largely depends on computer simulations, while the large-scale and long-term experimental data for energy use in buildings are yet to be carried out globally for different NBS. Future works should incorporate this experimental data to gain a better understanding of the holistic potential of NBS under different ambient environments. By incorporating wider study areas, more specific advice can be provided for cooling the urban environment, reducing building energy use and greenhouse gas emissions globally.